Hello students, in this video we will study bar magnet as an equivalent solenoid. You can see in the figure there is a resemblance of magnetic field lines for a bar magnet and a solenoid. So we can say that a large number of circulating currents is analogous to bar magnet. We know that the current loop acts as magnetic dipole or a bar magnet, and we have studied in our previous videos that Ampere had suggested that all magnetic phenomena can be explained in terms of circulating currents. So here in this video we will find the axial magnetic field of a solenoid, and then we will see it is similar to the axial magnetic field of bar magnet. Let us start. So what is a solenoid? We know that solenoid is a long cylindrical helix like this, made by winding closely large number of turns. When current is passed through it, magnetic field lines are produced around and within the solenoid. These field lines are uniform within the solenoid and are parallel to the axis of the solenoid, and its direction can be obtained by straight curled right hand rule. So we can say that it is similar to a bar magnet. So let us prove it. For this, a bar magnet can be considered as a large number of circulating currents like in solenoid. And if we cut the bar magnet in two smaller magnets, we will get two similar magnets but with weaker magnetic properties. Same is the case with solenoid. The magnetic field lines remain continuous and emerges from one end and reach to the other end of the solenoid, as in the case of the bar magnet. Also, if we place a magnetic needle near the bar magnet or the solenoid, the deflections are same in both the cases. So to demonstrate this similarity of current carrying solenoid to a bar magnet, let us calculate the axial magnetic field of a solenoid. For this, we have considered a solenoid of length 2L, and we will calculate the magnetic field at point P, which is at a distance r from the center of the solenoid. For this, we have considered a small current loop of thickness dx, which is at a distance x from the center of the solenoid. We have considered one current loop, but each turn of the solenoid behaves as a small magnetic dipole having dipole moment. That is, a number of small magnetic dipoles are placed in line all together, and number of small dipoles will be equal to number of turns in the solenoid. So the south and north pole of each turn in the solenoid will cancel each other except at the ends. So the entire solenoid can be replaced by a single north and south pole, which is separated by a distance of length 2L, that is the length of the solenoid. So in order to prove it to a bar magnet, we have considered one circulating current loop of thickness dx, which is at a distance x from the center. Let n be the number of turns per unit length of the solenoid. So number of turns in the element of length dx will be given by n times dx, as it is number of turns per unit length. So the number of turns in thickness dx will be n times dx. So the total magnetic field due to the current loop of radius a at point P on the axis which is at a distance r from the center of the loop, will be given by dB is equal to mu naught I a square into number of turns upon 2 times a square plus r minus x whole square raised to the power 3 by 2. See, we have considered a small current loop of thickness dx. So definitely at point P, the magnetic field will also be small. So that small magnetic field is written as dB. And we have obtained this expression from our previous video when we have considered that there is a current loop and we have tried to find the magnetic field at point P, which is at a distance r from the center of the loop having radius a. If you remember, we have calculated the magnetic field at point P in the similar way. Here the distance of point P from the loop of thickness dx is r minus x. So in the denominator we have simply replaced r square, which we have obtained in this expression, by r minus x whole square, because the distance of the current loop having thickness dx, which we have considered here, is at a distance r minus x from the point P. See here, this point P is at a distance of r minus x, because this is x and this is r. So in the denominator we have put down the distance as r minus x. As this distance is very large as compared to the radius of the solenoid, so we are neglecting a square from the denominator, and also this distance r is very large as compared to the distance x of the small loop from the center. So we will omit x also from the denominator, only from the denominator and from nowhere else. We cannot omit a square from the numerator, otherwise this expression, entire expression, will be 0. So what we will do, as compared to the radius r, we will neglect a as well as we will neglect x. So what we will be having in the denominator, if we will neglect a square as well as if we neglect this x, we will have simply this r term in the denominator raised to the power 3 by 2. So we will obtain it as 2r cube in the denominator, and rest of the terms in the numerator are copied as it is. Now this is the magnetic field generated due to a small current loop of thickness dx. So we have written it as dB, but in order to find the entire magnetic field, we have to integrate this term within the limits minus L to plus L in order to consider the entire length of the solenoid, which is 2L, because we are talking from the center of the solenoid. So considering the negative x-axis as well as the positive x-axis, it will become minus L to plus L, like this. So this will be the total magnetic field generated at point P due to the entire length of the solenoid, which is 2L. When we will integrate, we will obtain this expression. Putting down the limits, we will get this expression. Now in this expression, if I will multiply by the same term in the numerator and in the denominator, it will not make any change in the expression. So let us do it. While multiplying 2 pi in the denominator, it will become 4 pi r cube, and in the numerator the expression will be written like this. Now just rearrange these terms. I have written the terms like this, that mu naught upon 4 pi is written together and rest of the terms are written all together. Here I into pi a square is current multiplied by the area. And we remember that the magnetic moment is total number of turns into current into area of cross section. I hope you remember this formula which we have used earlier also, that the magnetic moment is total number of turns into current into area. So here the total number of turns will be N is number of turns per unit length. So total length is 2L. So the total number of turns will be N times 2L, and current is I, and the area of cross section is pi a square. So in the numerator of the earlier expression, we will put down this magnetic moment like this. So we have obtained the magnetic field expression as mu naught upon 4 pi into 2m upon r cube. And if we compare it with the expression of the magnetic field on the axial line of the bar magnet, which we have calculated in our previous video, we find that this expression is similar. So we can conclude that a finite solenoid carrying current is equivalent to a bar magnet. And this was our aim, that we have to prove that bar magnet is equivalent to a solenoid, that we have justified by calculating this magnetic field at an axial point. Thanks for watching. Please like, share and subscribe.